If you were to, I don't know, take an X-ray vision of a modern city block, right? And you were looking only for invisible forces, you'd see this crazy, chaotic, spinning web of dense magnetic fields, like millions of them.
Oh, absolutely everywhere.
Yeah, they're driving the elevators in the high-rises, you know, pumping water through the subterranean mains, spinning the hard drives in those massive server farms, and of course, propelling the electric vehicles gliding down the street.
It's basically the hidden infrastructure of our whole lives.
Exactly. And we tend to credit electricity for powering the modern world. I mean, it's the metric we measure, it's the utility we pay for, right? It's the thing we warn people not to touch.
Right, the danger element.
Yeah, but electricity itself it's just the supply line. The actual physical work, like the literal turning of the modern world, is handled by something entirely invisible and honestly, infinitely more subtle.
Well, we treat electricity as the main event because it demands our attention. We're
Yeah.
biologically wired to notice the flash of an arc or the loud hum of a high voltage line.
We like flashy things.
We do. We focus on the conductor, the battery, the plug. But the electric current is, like you said, it's merely the fuel. The prime mover, the actual mechanism that converts that electrical potential into physical kinetic energy, is the magnetic field.
Which brings us to today's deep dive. We're looking at an excerpt from Lev Naimodin titled Magnetic Mystery, and the core thesis here is a really vital shift in perspective for anyone interested in mechanics or physics.
Yeah, it's such a great text. The main takeaway you really need to keep in mind today is this. Electricity flashes, but magnetism turns.
I love that. Electricity flashes, but magnetism turns. So our mission for this deep dive is to isolate that magnetic field from the electrical system that generates it. We want to look really closely at the physics of how an invisible field crosses empty space to generate just, well, massive amounts of torque.
And to get there, we kind of need to bypass the wiring and the power electronics and look directly at the actual geometry of the motor itself.
Right, so let's shrink down. Imagine you're climbing inside an unplugged electric motor. Most of you are probably intimately familiar with the basic architecture here. There's a stationary housing wrapped in copper that's the stator.
Right, the part that stays static.
Exactly. And it surrounds a rotating central shaft, which is the rotor. The fundamental engineering problem is getting that inner rotor to turn without physically touching it.
Which is entirely a spatial challenge. I mean, when you pass an electric current through the copper windings of the stator, you generate a magnetic field. We've understood that relationship for, gosh, well over a century.
Right. Moving electric charges induce magnetic fields. Physics 101.
Exactly. But here's the catch: a static magnetic field is functionally useless for continuous motion. If you just energize the stator with a direct current, the magnetic field just locks the rotor into a single alignment.
It just freezes.
Right? It behaves like a brake, not an engine. So, to generate continuous rotational torque, the magnetic field itself has to actually move.
And Naimodin uses this brilliant visual analogy in the text to explain how engineers pull this off without physically spinning that heavy outer stator. He compares the manipulation of the magnetic field to spectators in a stadium performing the wave.
I love that analogy. It's an incredibly precise way to model magnetomotive force. Because think about it, when you watch a stadium wave from a distance, you see this distinct, coherent peak of energy traveling around the arena at high speed.
But the people aren't running around the stadium.
No, not at all. Every single spectator is fixed in their specific seat. They're just standing up and sitting down in a really carefully timed sequence.
So the physical components are totally stationary, but the energy pattern they generate is in constant high-speed motion.
Exactly. And translating that back to our stator geometry, those individual seats are the stationary copper coils wound around the iron core. By feeding alternating current into those coils, engineers phase shift the timing of the electrical pulses.
Like coordinating the fans standing up.
Yes. The current peaks in one coil, then the next, perfectly mimicking that sequence of the stadium wave. The physical copper never moves a single millimeter. But the resulting magnetic flux vector, this invisible wave of magnetic force, sweeps around the inner circumference of the stator.
And then the rotor, which is suspended right in the center of this spinning magnetic wave, is effectively dragged along by the moving flux. I mean, it basically wants to align with the magnetic field, but because the field is constantly racing ahead of it, the rotor is just caught in this perpetual state of chasing.
It's endlessly chasing that wave. And that constant magnetic pull is what generates rotational motion. That's the torque.
Which we see as, a spinning desk fan or a power drill or the drum of your washing machine.
Yeah, and the variation between different types of motors, like whether the rotor spins slightly slower than the magnetic field or in perfect synchronous lockstep with it, that just comes down to how the rotor itself interacts with that spinning flux.
But the underlying physics remain identical, right? Regardless of the specific motor topology.
Completely identical. You're generating a rotating magnetic wave, and you're using it to apply torque to a mass. And this actually introduces the central physical dilemma of the electric motor.
Right, because torque is being applied, heavy physical work is getting done, but there is absolutely no mechanical linkage between the source of the force and the object being moved.
None. There are no gears, there are no belts, no fluid
You're
coupling.
just a magnetic field crossing a literal void.
Yes. And we need to focus entirely on that void, because the space between the stator and the rotor is arguably the most critical dimension in the entire machine. In engineering, we call it the air gap.
The air gap, it's just the physical clearance that allows the rotor to spin freely inside the stator housing. I mean, if you stripped away the casing and looked at a cross-section of the motor, the air gap literally just appears as a microscopic ring of empty space.
And functionally, it looks like absolutely nothing.
But according to the text, it is the most important nothing in the machine.
It is the most heavily engineered nothing in modern mechanics. That tiny volume of air is the bottleneck of the entire system. Because, well, while air is a physical gas, magnetically speaking, it is a massive barrier.
It resists the magnetic field, right?
Hugely.
Right.
Air has incredibly low magnetic permeability, meaning it heavily resists the flow of magnetic flux. Engineers refer to this resistance as reluctance. The magnetic wave generated in the highly permeable iron of the stator desperately wants to just, stay in the iron.
So forcing that flux to jump out of the stator, cross that air gap, and enter the rotor, that requires a massive expenditure of electrical energy.
Exactly. The inverse square law is just brutal here. The magnetic field strength drops off exponentially the further it has to travel through that high reluctance air gap.
Okay, so from a purely magnetic standpoint, the solution seems super obvious. You just want the air gap to be as microscopically thin as possible. Like, you'd want the stator iron and the rotor iron practically kissing to minimize that reluctance and maximize the torque transfer.
That is the absolute magnetic ideal. If you could engineer an air gap of, say, 0.001 millimeters, your motor's efficiency and power density would just skyrocket.
You could build incredibly small motors with staggering amounts of horsepower.
You could. But the mechanical realities of the physical world make that completely impossible. The magnetic ideal totally ignores thermal dynamics and material science.
Right, because you have this heavy metal rotor spinning at 10, maybe 15,000 revolutions per minute.
And at that speed, centrifugal force is actively pulling the mass of the rotor outward, causing it to physically expand in diameter.
Oh, wow. So it literally gets wider as it spins faster.
Yes. And beyond that, the electrical resistance in the copper and the magnetic hysteresis in the iron, that generates massive amounts of heat.
Yeah.
And what happens when metal heats up?
It expands.
Exactly. We're talking about operating temperatures that can easily exceed 150 degrees Celsius. And you also have to account for bearing tolerances. No bearing is perfectly rigid. There's always a microscopic amount of radial play or run-out as the shaft spins.
Okay, so you have a rotor that is swelling from centrifugal force, expanding from extreme thermal loads, and vibrating within the mechanical tolerances of its bearings.
All at the same time.
So if an engineer designs an air gap that is too tight, like just a tiny fraction of a millimeter just to chase that magnetic efficiency, it seems like a disaster waiting to happen.
It is. The moment that motor hits peak operating temperature, or say, hits a pothole that rattles the chassis, the rotor is going to expand or deflect just enough to physically contact the inner wall of the stator.
And at 15,000 RPMs? Wait, what actually happens in a stator rotor strike?
Oh, it's not a minor mechanical failure. It is the instantaneous, catastrophic destruction of the machine. The friction basically welds the laminations together, the copper windings short out, and the motor effectively tears itself apart from the inside.
Jeez. So the engineer is trapped in this huge paradox. Make the gap wide enough to ensure mechanical safety, and the reluctance skyrockets, which kills your magnetic efficiency. But make the gap tight enough to maximize torque, and the machine is a ticking time bomb waiting for a thermal spike to just destroy it. How does the industry even balance that?
It requires a level of manufacturing precision that honestly borders on the obsessive. This is where electrical engineering gives way to high-end metallurgy and machining. The modern air gap isn't simply a compromise. It's an aggressively controlled environment.
What does that mean in practice? Like, how do they control it?
Well, engineers use incredibly high-grade electrical steels that are specifically alloyed to minimize thermal expansion. And instead of solid blocks of metal, both the stator and the rotor are built from hundreds of razor-thin laminations.
Stamped out of sheets.
Yeah, stamped with microscopic precision, and that helps manage the heat distribution. They also actively manage the thermal loads through advanced cooling jackets, literally pumping liquid coolant directly through the stator housing to lock the thermal expansion curve in place.
That is wild. And what about the spinning expanding part, the centrifugal force?
For that, they use carbon fiber sleeving wrapped really tightly around the rotor to counteract the centrifugal expansion,
Yeah.
physically constraining the metal from growing outward at those high RPMs.
So by meticulously controlling all these mechanical variables, the heat, the structural rigidity, the bearing stiffness, manufacturers can safely push the air gap down to tolerances that would have seemed completely suicidal a few decades ago.
Absolutely. We are talking about maintaining a consistent gap of under half a millimeter across the entire length of a rapidly spinning, heavily loaded rotor.
Under half a millimeter.
Yeah. And the ability to hold that tolerance under extreme physical duress is the dividing line between those heavy, inefficient industrial motors of the past and the incredibly dense, lightweight power plants driving modern technology today.
And when you achieve that microscopic air gap, right, when you force that dense magnetic stadium wave to cross that tiny threshold of air, the resulting physical force is just immediate and staggering.
It really is.
We see the final product of this engineering out in the real world, I mean, most notably in the acceleration of a modern electric vehicle. Anyone who has driven a performance EV, you know that the delivery of power feels entirely different from a traditional machine.
Oh, night and day.
Mm-hmm.
It doesn't just feel faster. The actual physical sensation of the torque delivery feels fundamentally altered.
Why is that? I mean, structurally, why does it feel so different?
Well, it feels different because you are bypassing the entire mechanical supply chain of a traditional powertrain. Just consider the torque curve of an internal combustion engine.
Okay, an ICE.
Right. An engine requires air and fuel to generate pressure. At 0 RPM, the engine is producing zero torque. To generate pushing force, the engine basically has to mechanically breathe.
The valves have to open, the pistons have to draw on air.
Exactly. The combustion sequence has to occur, and the resulting physical explosion has to push a piston down. Then that piston turns a crankshaft, which transfers force through this complex array of gears in a transmission, which eventually finally twists the axles.
So an internal combustion engine has this huge mechanical latency. You press the accelerator, and you can practically hear the machine working through that sequence.
You hear the intake, the rising RPMs, the mechanical strain as the engine builds up to its optimal power band.
Mm-hmm.
You literally feel the delay between the request for power and the physical delivery of torque.
But in the electric motor, that mechanical latency is just eliminated completely.
They're totally gone. The moment the computer signals for acceleration, the power electronics switch the current into the stator coils. The magnetic field propagates at the speed of light. The flux sweeps across that microscopic air gap instantly.
Instantly.
Yes. And because the stator is fully energized immediately, the maximum magnetic coupling occurs at 0 RPM. The motor is capable of delivering its absolute peak torque from a dead stop.
Wow, so there's no mechanical breathing required. The magnetic wave doesn't need to build up momentum.
None at all. The rotor is simply locked in the invisible grip of the magnetic field and twisted with maximum force right from the start.
And the silence of the system heavily amplifies this sensation, doesn't it? Without the rising roar of a combustion sequence or the vibration of pistons, the sudden onset of massive G-forces feels almost, well, supernatural.
Supernatural is a great word for it. It feels detached from the physical rules we're used to experiencing in vehicles.
It really challenges our intuitive understanding of cause and effect. We expect a massive physical output to require a loud, violent mechanical process.
Right, but the electric motor proves that extreme mechanical violence is actually unnecessary. The magnetic field was always capable of this instantaneous force. We simply lapped the manufacturing precision to bring the stator and the rotor close enough together without touching to fully harness it.
So the supernatural feeling is just electromagnetism operating without mechanical interference. It's the raw conversion of energy.
Exactly. And while we heavily associate this sensation with high-end automotive engineering, Teslas and whatnot, the exact same principle is quietly operating in the background of our daily lives everywhere.
Oh, for sure. Like the washing machine aggressively reversing the direction of a heavy, soaking, wet drum of clothes in a fraction of a second.
Yes. or industrial water pumps instantly snapping to full pressure, or even a drone hovering with these microscopic adjustments to its four rotors, reacting to wind currents way faster than a human pilot could ever process.
The underlying mechanism is universal. We perceive the spinning blades, we see the rising elevator, the turning wheels, but the physical objects are just the downstream result.
They're just the artifacts, yeah. The real work is being done by the magnetic flux bridging the air gap.
Which fundamentally reframes how you should view the machinery around you. I mean, the copper wiring, the lithium-ion batteries, the massive power grids, they're just the infrastructure required to feed the system.
They don't turn the gears.
Right. The prime mover is the invisible magnetic wave racing around its iron track. The turning of the world is dictated by a force we cannot even see, crossing a gap of empty air less than a millimeter wide, completely devoid of mechanical linkage.
It's beautiful, really. And the progression of this technology forces us to ask, well, what happens when we reach the absolute physical limits of that system?
What do you mean, like making the air gap even smaller?
Sort of. I mean, we spend massive amounts of engineering capital trying to shrink the air gap to overcome the reluctance of empty space, right?
Yeah.
But the iron core itself has a fundamental ceiling.
Okay.
It's called magnetic saturation.
Yeah.
Basically, there is a physical limit to how much magnetic flux you can cram into a given volume of electrical steel before the metal simply cannot carry any more energy.
Oh, so it just maxes out?
Exactly. Once the stator teeth hit saturation, pumping more electric current into the copper coils doesn't generate a stronger magnetic wave. It just creates massive amounts of waste heat.
So you just hit a wall.
A literal physical wall. So the provocative frontier of this engineering isn't just, cutting the air gap tighter. It's the pursuit of superconducting materials that can operate at room temperature.
Wait, to do what?
To eliminate the iron core and the air gap entirely. Imagine a motor where the magnetic wave isn't constrained by the physical limits of metal at all, but operates in a frictionless state of infinite magnetic density.
A motor with no iron core. Just pure magnetic force.
Yes. That is the threshold where the physics stop looking like engineering and start looking entirely like magic.
Wow. That's something to think about the next time you turn on a simple desk fan. You're just watching the ghost in the machine.
Well, that's going to do it for our deep dive today. Remember, next time you switch on an appliance, don't just look at the spinning plastic blades. Picture that invisible magnetic wave racing around its narrow circular track, turning the physical world without any hooks, ropes, or magic hands. The mysterious hidden mover is always there.